On May 28th, Blue Origin's new rocket booster had a catastrophic failure during a routine engine test. The explosion damaged Launch Complex 36 and wrecked the main launch tower. It was a mess. The transporter erector gantry, which lifts the massive rocket into place, was severely warped by the heat. This single event instantly stalled Jeff Bezos' plans to test the Blue Moon lander before the decade ends. Almost immediately, people on space forums suggested a backup plan. Why not just put Blue Origin's moon lander on a SpaceX Falcon Heavy? The logic seemed simple. SpaceX is already flying heavy payloads, and their rockets are reliable. Tech channels started calling it a genius backup solution. But rockets don't work that way. In aerospace, things that are almost compatible are actually completely incompatible. The media treats rockets like Lego blocks that you can swap out. The reality is that swapping launch vehicles is an engineering nightmare that violates basic physics. On paper, Falcon Heavy seems like a viable option. It is a proven heavy lifter. But once you look at the actual physics, the idea falls apart. To understand why, we have to look at the hard parameters. It comes down to mass, volume, and chemistry. Most commentators missed the engineering details, but they matter. If you ignore the physical constraints, you are just designing a very expensive firework. Let's break down the 3 physical barriers that make this launch swap impossible. First, consider the mass. The Blue Moon lander is a massive machine. When fully fueled, it weighs 45 metric tons. That is 99,000 pounds. Most of that mass is liquid hydrogen and liquid oxygen. You need all of that fuel to descend to the lunar surface and return the crew back to orbit. Now look at Falcon Heavy. If you expend the entire rocket, meaning you do not recover the side boosters or the center core, its absolute limit is 24 tons to a trans-lunar injection trajectory. If you try to recover the boosters, that capacity drops significantly. That leaves you with a deficit of 21 tons. It is not even close. You are trying to lift a semi-truck with a mid-size SUV. Some suggested launching Blue Moon empty and refueling it in orbit, but Blue Moon is an integrated vehicle. You cannot launch its fuel tanks empty because it does not have the docking ports or internal pumps to transfer super-cold liquid hydrogen in space. SpaceX solved this mass problem for Starship by planning a massive orbital refueling campaign. But Blue Moon wasn't built for orbital docking or fuel transfer. It lacks the internal plumbing, insulation, and docking hardware to do orbital refuels on Falcon Heavy. It is built to launch fully loaded on a single newglenn. Then you have the physical size. Spaceflight is as much about volume as it is about weight. Blue Moon folds down to fit inside newglenn's massive 7-meter fairing. It needs that wide envelope because of its landing legs and giant solar arrays. Falcon Heavy's standard fairing is only 5.2 meters wide. If you try to stuff Blue Moon inside, the landing pads physically hit the metal walls. Redesigning the lander to fold tighter would require rebuilding its entire structural frame. That is a process that would take years and hundreds of millions of dollars. Could SpaceX just build a 7-meter fairing for Falcon Heavy? Technically, they could build the composite shell, but flying a giant 7-meter bulb on top of a 3.7-meter rocket core creates massive aerodynamic issues. During max Q, the point of maximum aerodynamic pressure, the drag on that oversized fairing would create immense bending forces. It would likely crush the connection joints and tear the rocket apart. Finally, consider the chemistry. Rockets are not just vehicles, they are extensions of their launch pads. Blue Moon runs on liquid hydrogen. It is stored at -253 degrees Celsius. Handling it requires specialized vacuum-insulated lines, complex boil-off management, and massive flare stacks to vent explosive hydrogen gas safely. Falcon Heavy's launch pad at LC-39A has no liquid hydrogen infrastructure. It is built for kerosene and liquid oxygen. There are no hydrogen lines running up the transporter erector to feed the lander's tanks before launch. Rebuilding the tower to add hydrogen plumbing would cost tens of millions of dollars. More importantly, a pad conversion would require shutting down LC-39A for over a year. That would halt all Falcon Heavy flights and crewed Falcon 9 missions to the space station. SpaceX would never sacrifice their primary launch pad just to help a competitor solve a booster problem. Even SpaceX's Raptor engines use methane and require different launch mounts. You cannot mix and match cryogenic plumbing on a whim. The engineering reality is that a launch pad is custom tailored to the rocket. If you change the fuel, you change the pad. There is no easy shortcut here. Jeff Bezos cannot buy his way out of this with a SpaceX flight. Blue Origin has to rebuild LC-36, fix the New Glenn booster, and fly it. The race to the moon is not about PR. It is about hard engineering. But SpaceX has its own problems. Their new Raptor 3 vacuum engines are showing unexpected performance drops after Flight 12. I wonder how they will fix this. If you want to see how this affects SpaceX's own lunar refueling timeline, that is the subject of our next video.